What's up everyone? Today I'm gonna show you how to execute shellcode in memory and how to reduce its detection rate by encrypting it with XOR and AES algorithms. Also, if you have something that you would like me to cover in future videos, write it down in the comments. But without further ado, let's get started. So that's how the shellcode loader looks like. Let me zoom in a little bit. First, we need to include windows.h. You don't need any other libraries. You don't need stdio. We are not printing or reading anything, so windows.h is enough. Unsigned char shellcode. This is a shellcode generated with MSF Venom. You can see the exact command is this. So architecture x64. Interpreter reverse TCP, payload, lhost lport, exit func thread, and format C. Of course, this command is in the description, so you can copy paste it. Then we are allocating memory, allocating a new buffer with virtual alloc. This is a Win32 API function, by the way, and it's documented in Microsoft's WinAPI documentation. This is the best resource you can get for working with Windows API, and you will see yourself jumping back and forth as you progress with your malware development journey. But it's not used, of course, only for malware development. So, but yeah, virtual alloc. It takes 4 parameters: LP address, DW size, FL allocation type, and FL protect. So LP address is the starting address of the region to allocate. If the parameter is null, the system determines where to allocate the region by itself. We are passing null here. We want system to deal with it. Second parameter is the size of the buffer that you want to allocate. We pass shellcode +1, size of shellcode +1. Third parameter is the allocation type. So we are using 2 allocation types together: memory commit and memory reserve. Let me start with reserve. So it reserves a range of the process's virtual address space without allocating any actual physical storage in memory or in the paging file on disk. You can commit reserved pages in subsequent calls to the virtual alloc function. To reserve and commit pages, this is what we want. In one setup, call virtual alloc with, as you can see, memory commit and memory reserve. That's what we are doing here. And the last, FL protect parameter is the memory protection for the region of pages to be allocated. If the pages are being committed, you can specify any one of the memory protection constants. We want first to pass page read write, as we will be writing to this buffer. But then after we copy our shellcode to it, we will change, as you can see with virtual protect function, we will change the FL protect to execute read write. So, but before that, let's actually copy the shellcode to just allocated buffer. Very simple function: memcopy, destination, source, and size. Just 3 arguments, very straightforward. Next thing, the virtual protect function. You pass 4 arguments: the buffer that you are referring to, size of this buffer, size of the payload, sorry. Page execute read write, that's the new protection, and the pointer to the variable that will receive the old protection. So you just create a new variable, assign it to null, and point to it here. So we have set up, we have set up the shellcode in memory, and now we create a new thread with it, so to actually execute it. So handle hthread create thread function. It takes 5 parameters, but as you can see, six parameters, but you can see we are specifying in details, sort of only one, but let me show you what the other do. Create thread. It may not pop immediately, but it is there, right here. Okay. Thread attributes. If thread attributes is null, we cannot. The handle cannot be inherited. So this is basically a pointer to a structure that determines whether the return handle can be inherited by a child process. We don't need that at all, so we just pass null. LP security descriptor member of the structure specifies a security descriptor for the new thread. If it's null, the thread gets a default. Oh, sorry, that's the same parameter. That it's not relevant for now. Stack size. We pass 0, we wanted to use the default size for the executable. LP start address, that's where we actually pass the, our buffer pointer to the buffer actually. So this is the start address where of the shellcode in memory. LP parameter, a pointer to variable to be passed to the thread. As you can see, it's optional, and we are passing no variables, so null here. Then DW creation flags. We are passing 0 because we want the thread to run immediately after creation. We don't want to suspend it or do anything else with it. And the last parameter is null because it is thread ID. If you can pass there a pointer to a variable, and this variable will receive the ID of a thread, but we don't need to do anything with the thread ID, so let's just pass null here and don't bother with the thread ID. Last thing, wait for single object. This function will it takes two parameters, the handle to a thread and the timeout, sort of, because we basically want it to wait for the thread to finish. So once this finishes, our script will finish. It keeps it running basically, and just for cleanup, you can close handle after finishing working with a thread. Okay, so that's it. That's the full code. Let's see it in action. So to test the payload, we're gonna fire up MSF console and use multi-handler to catch our shell. Use multi-handler. Let me just quickly copy the payload like this, set payload, then set lhost to IP of my Kali machine, 192.168.0.130, and I think we are good to go. Executing processes, okay, everything is right. So run -j to run as a job. As you can see, it started reverse TCP handler on this IP end port. Now when you go back to the code and run it, it will hang, and in the Metasploit you will have a new session opened. So sessions 1 shell. You can see I'm inside my Windows machine right now. I can type who am I, so you see it works. Okay, so as you might be expecting, the MSF Venom payload is extremely popular and very well signatured. I think I can say it this way. So pretty much every decent antivirus will catch it. I can show you that if you run it through VirusTotal, it will be flagged by, hopefully, most vendors. Let it work. Oh, as you can see, Windows Interpreter, it immediately catches it. Okay, we got 24, 27. Actually, I was expecting more, 28. Okay, but still, very well flagged. Avast already knows, immediately knows that it is MSF shell. What about Windows Defender? Where are you? Microsoft Interpreter. Okay, so it is extremely recognizable. Let me show you how you can slightly, but still, reduce this detection rate just by encrypting the shellcode with XOR and AES algorithms. And then we're gonna compare how well XOR encryption works and how well AES encryption works in terms of reducing detection. But first we need to write the script that will encrypt our shellcode. Let me show you how this script looks right now. Actually, before we dive into the Crypter code, let me tell you about static detection and how it works. So when antivirus scans a file, it looks for known sequences of bytes that can uniquely identify the malware. It tries to match it with one of pre-built rules. Most common detection patterns are YARA rules, which can be fully customizable to identify targeted attacks and security threats specific to your environment. So basically, if your AV sees bytes like this, it will know that it's dealing with Metasploit x64 reverse TCP, just like you saw in VirusTotal scan. Before I start describing each function, let me zoom in actually, you need to download two files, AES.C and AES.H. These are both from Tiny-AES library, Tiny-AES. Their GitHub repository, link to this will be in the video description. Just open up those two, click raw, and can Ctrl+C all the text. So that's it. And also remember to include it with between quotation AES.H. Okay, so first we define key size and IV size. This is for AES encryption, and we are generating key like this and IV like this. So IV, this is something that makes it impossible for two identical plaintext values to generate the same ciphertext. So thanks to IV, from let's say word generate, if you take two words generate, they won't encrypted with key and IV, they won't generate the same ciphertext. So they will be, for first generate, there will be one ciphertext, and for the second one will be second ciphertext, no matter that they are exactly the same. So I hope that's understandable what I just said. So those two functions. Then we will require padding for some payloads, because AES Tiny-AES-C requires encrypted text to be encrypted to be dividable by 16. So if it's not, you need to add some bytes to make it of size, for example 512, as we will do with our shellcode. Then there is a function XOR encrypt that just performs XOR encryption with XOR key. Here's XOR key, unsigned char key, my secret XOR key. Again, MSF Venom payload, the same as before. First we need to, this is the AES encryption part. So we have to initialize a struct, add padding, shellcode and shellcode size. By the way, this shellcode is 511, so it will add it will add 1 byte to make it 512. We are starting encryption, initializing two variables, pointer key and pointer IV. You have key size and IV size respectively. Here we are generating a seed for the run function here. So that generate key and generate IV, they won't be the same. Also we are XORing time. We are adding first value from key to the seed to make it more random, sort of. Next thing, generating a key. Okay, so here it was generated. Here we are just printing into the screen, and the AES encryption itself is beginning here. It's starting here. So first AES init ctx AV. We are initializing the function with pointer to our structure, pointer to struct, with a key and IV, and here we are encrypting our buffer. Again, pointer to struct, shellcode and size of shellcode, and this for loop prints the encrypted shellcode, and then the encrypted shellcode is then XORed. We XOR with the key, with this key, and you can see it being printed here, and also encrypted shellcode size. So I think it's pretty straightforward how it works. And let's see it in action. So if you run it, this will produce this error, because this error is because of how I handle padding here. As you can see, the padding is applied to the shellcode variable after it's created. So there is 511 bytes of memory reserved for this, and we are adding one more, and that's not really how you should do it technically, but I decided to not bother with this error because it doesn't our program still works, but you shouldn't be doing it this way. But yeah, don't bother right now. And as you can see, generated key, generated IV, AES encrypted shellcode, and then XORed shellcode. So as you might have guessed, we will be using this one, this encrypted shellcode, instead of the plaintext shellcode in our loader. And as you might have guessed, we will need to reverse this process. So we will first de-XOR it, decrypt, so de-XOR it and get this AES encrypted shellcode, and then again with Tiny-AES-C library, we will decrypt it using key and IV. So let me show you how to modify the loader to do so. Okay, so I have already included the AES.c and .h files, so we don't waste time on this. And let's start by copying the encrypted shellcode. Okay, like this. Great. Now let's create unsigned char AES key, and also the same for IV. Like this. IV. Okay, and we need to copy them too. First, second. Okay, we should be good to go now. Great. Now, okay, actually, let me copy from the encryptor code. Let me copy one more thing. We will need to copy the AES key, the XOR key, and maybe, so we don't waste time, let's copy the XOR encrypt function. Okay, because the XOR encrypt is the same as XOR decrypt. We are decrypting it the same way. Okay, so what we need to do is, remember, we first encrypted with AES, then encrypted with XOR. So now we need to first decrypt with XOR, using XOR, and then decrypt using AES algorithm, right? So size of shellcode, key and size of key, like this. Now we need to again initialize this struct, AES CTX struct, like this, CTX, AES init, what's wrong, AES init, something is wrong. What's wrong? CTX. It should be okay. Incomplete type is not allowed. What do you mean? Oh, okay, I forgot to... see, I forgot to include... AES.h here. So, once you do that, you should... Okay, see, no error. So now AES init CTX IV, pointer to CTX, CTX AES key, and AES IV, like this, and AES CBC decrypt buffer. Again, pointer to CTX struct, shellcode, and size. Size of shellcode. Okay, I don't want to print it here because we will need to include another library, and that's not necessary. But basically, this is how the decryption on runtime looks like, and this is the same. So let me now run with the same options. Let me run as a job, or maybe it's already running, I don't remember. Jobs? No jobs. So run -j, TCP handler, and let me compile our new loader. Like this, and as you can see, it's running, and we got a shell. Sessions. You can see that we are indeed inside my PC, Windows PC again. But let's check if something changed in terms of detection rate. Let me go to virus total once again and open up run shellcode.exe. Hopefully we will get will be a little less detectable. Okay, we already have 20, 25. How much was it before? I don't remember. I'll need to check. It's 28 now. Okay, so not a really good score, as you can see. It didn't help pretty much at all. But what differs from a previous scan is that we have different detection responses from antiviruses. So as you remember, previously we had, for example, from AVG, MSF Shell, Avast, MSF Shell, where is Microsoft? Or Windows Defender, Interpreter, and basically it was being recognized as something that's coming from Metasploit framework. But when we encrypted the payload, as you can see, Avast is no longer seeing anything MSF related. Same goes for AVG, Microsoft, no Metasploit. The only antivirus that detects Interpreter is AHN Lab. I don't really know them, but apparently they are quite good. but yeah, so you can see that we are being detected, but as a shellcode runner only, and not because of our payload. So that's something. But we could go even deeper. If you don't want to see this shellcode running, because it is pretty obvious that if you are using virtual alloc and page execute read write, it's very rare. It's very rare if a thread has if a buffer has execute, read and write permissions, all three. It's not a good sign for any antivirus solution, and it will probably flag it immediately. So what can we do? We can use, for example, native API instead of Windows API. It's a lightweight, low-level API. It's even older than Windows API because it was used in Windows NT, but it is undocumented. It's some people call it hidden API, hidden API. There's no official, little or no official documentation. There is some functions are documented by reverse engineers who were committed enough to figure out what certain things do. But yeah, this is definitely an advanced topic, and I might make a video about it in the future, but I will have to learn it myself first. But yeah, I think it's all for today. Thanks for sticking to the end, and I hope you've learned something today, as I did. Also, check out my other videos about malware development. They are somewhere here. And be sure to follow me on Twitter so you are always up to date with the new videos. See you soon.